Okay. Xsens Vision Navigator, we just launched last December, and now this is the first time we give the training on the product itself. So I'm Brian, based from Shanghai office, the customer support manager for APAC region. Okay, let's go ahead. So this is a new technology. We have the visual. Yes, by the way, it's recorded. So it's already recorded automatically. And if some of your colleagues are not able to join, you can just replay it. Yeah. Okay. So this is a new technology. This is we call it a visual inertial odometry (VIO). It's a combination of the inertial sensor, the camera, and also the GNSS INS. There is a image. For example, when this sensor is over here, it takes some image, and then when this sensor moves to another position, it takes another image. So based on this triangle calculation, some algorithms between there, you can get the position very accurately, and it is dependent on the distance itself, not the time. So what the XVN wants to solve is that it wants to solve the global positioning in GNSS denied and unknown changing environments. So for example, in these autonomous driving testing cars, they want to go through these bridges, buildings. There are some areas, there are a lot of trees, plants, and those this can really degrade the performance of the GNSS. And also, if there are skyscrapers, the buildings, this can also the GNSS signal can also be reflected. So for this technology, we don't really need the pre-recorded map. We don't need our customer to subscribe to those very high accurate maps for navigation. Okay. As you have seen this before, in the past, we have the MTI series, we have the gyroscope, we have the accelerometer, we have the magnetometer, and the GNSS barometer. That would be the MTI, for example, 670, 680G series. Now we add this visual sensor in there, the camera in there. Still on top of that, we need to do the sensor fusion. And for this device, you will have two antennas. And the two antennas are both working with the RTK mode. So you will have two antennas, both get RTK fix. After that, you can get the position of output. So this sensor can operate from 0 kilometers up to 80 kilometers per hour. The restriction on the 80 kilometers is because when you are in the area, when you really depend on the camera itself, then 80 kilometers is the limit, because the camera itself is not fast enough to process this speed. But on the GNSS INS side, 80 kilometers or even more wouldn't be problems. Now the position is 1 centimeter plus 1 ppm, which is based on the condition on the RTK fix. The position error during the GNSS outage, which is 2% of travel distance. And if you use the wear odometry input, the wear speed sensors, the error could be reduced to 0.75%. And the orientation for roll, pitch, and yaw or heading will be less than 0.4 degrees. The velocity accuracy is 0.1 meters per second. The output rate up to 200 hertz. There are some other features, for example, time synchronization. So this device, there is a pin over here called Ethernet. So basically, if you plug this device into your router, then this device can be visited from any device from this local area network. So basically, you can also visit this UDP ports and to get the timestamp. So synchronize via this called NTP, the network time synchronization protocol. Also, it also provides the option like the traditional way of time synchronization. For example, it can provide the time parse like the PPS that MTI 680 or 630 can provide, which is a sync out. Also, in the syncing PPS, if some other device trigger this device, and on the syncing side, you can get the timestamp, which is called a time mark. And the output itself is not using the XBus, so it is using the ASIC, so basically the stream report. And there is also ROS and a ROS1 and a ROS2 driver for there. So something we need to notice that is for this device we have to firstly take this device outside to have very good GNSS receiver, and after that you get both RTK fix for both antennas. After that you are able to get the sensor fusion output. Before that you don't have sensor fusion output, which means the every time you have to start this device outside where there's a good GNSS reception. Otherwise, it's not about possible to output any sensor fusion data outputs. But there is a plan that in this first half we're gonna add a new feature. We plan to add a new feature, which is you can actually set up a QR code at some specific location where the location is known. So basically, you can start this device, start to send the sensor fusion output at the beginning, even it is indoor. So imagine that you have a very accurate position indoor in the warehouse, and there is a QR code which stands for the location of this QR code. And then when you start fusion of this device, this device will take picture of this QR code, and then it knows that the starting point of this device is with some latitude and longitude. So for now, you have to take this device outside to get it RTK fix for the both antennas. After that, you can get data sensor fusion output. Also, in the future, there's also optional service like the post processing. Also, the point perfect, which is an advanced GNSS augmentation data service. All right, so the application would be, for example, a lot of outdoor. But with outdoor application, you have a lot of GNSS outages, or you have applications that then you are getting inside and outside the warehouses. So, for example, you can do this lawn mowing and the shuttling, delivery, inspection, cleaning, and also the mining and port logistics, agriculture. So just find the areas that when you are not able to have very good GNSS receiver. Actually, for autonomous driving, as long as you're not driving really fast, I think this is also a very good device. I will share some testing videos almost in the end, because I was actually driving this car, but not really fast, but the result was really, really good. So you can see here, these are the testings in different places. So for these red points, red areas, these are the areas when you don't have any GNSS receptions. But this XVN can really very well track the position. There's also almost no drift from these maps. You can see from these areas. Okay. At the Xsens headquarters, we also done this testing. So basically put the XVN on top of the car. On top of that, that would be the MTI 680G. And we were driving around in this area. So this area would be the GNSS denied area, like underground. And on top of that, they have also done a lot of testing. For example, here we have done 79.2 kilometers drive, and out of which there's a 30.2 kilometers, which is a 38.1% of the total distance, and there is no GNSS reception. So the average outage length is about 160 meters, and the average velocity is 14 kilometers per hour. That is not really fast. So these tests were done in a wide variety of environments, including the roads, university campuses, old town, narrow streets, busy business centers, with high rises in a multiple level parking garage. So the data, that is the result. We can see on the first line, first row, that would be the Novatel. That's a high-end GNSS receiver. So you can see the error in terms of the error of distance traveled. That is 5.7% on the mean, and for the medium value, that's 2.2%, and standard deviation is 11.9. For the U blocks F9R, that's 4.9, and 2.6, 9.9. With the Xsens Vision Navigator, the mean error is 1.5%, and the medium value is 1, and the standard deviation is 1.9. So you can see these areas. This is a parking lot. You don't have a good reception. And XVN plus WIRS, WS, which stands for WIR speed. So if you connect the WIR speed to the XVN, the result will be much more better. So you can see here, the GNSS itself was actually jumping around, but this Xsens Vision Navigator Vision output is really accurate following this map. So next, we're gonna introduce this product, how to use it, configuration, etc. So there's a prerequisite of the best performance of the XVN. So for example, firstly, we need to mount the antennas and sensors firmly to the mobile agents with respect to each other. Avoid unnecessary vibrations and interference from other signal sources. Guarantee the antennas have a full view of the sky. Also keep the distance between the antennas greater than 50 centimeters. So from antenna 1 to antenna 2, you need to have certain distance. So ideally would be greater than 50 centimeters. Also, if you install a sensor which has a deviation, there is a deviation from this antenna to this device. So actually in MTI 680G, we call it a GNSS lever arm. So basically you have to measure the distance, like, so this is the X axis. So you need to measure the distance from this point to this point on the X axis, on the Y axis, and on the Z axis. So you have to measure that distance and then fill into the setup on the XVN. And on the camera side, so make sure that there is a very nice view. For example, if your camera is just going down, then like half of the picture is occupied by the car engine itself. That's not good. So you need to have very good view of the front, and also please don't raise this device too much. Then you can only see the sky, which you cannot see the road. So basically, keep the view very straightforward and not too much of the car, not too much of the sky. Then you can see the front very easily. On the interfaces, on this device, we have the so you can see here. So basically, on this end, you have the Ethernet cable. So the Ethernet cable, and then you have the I/O cable and the aux cable. Then that's the power. So on the Ethernet, so basically it's just like a computer. You know, you plug in the Ethernet cable to the router, then you're able to visit this device via the IP address. And on the IP address, there are a lot of ports. On different ports, you can get different data or functions. And on the UART, so that would be on the IO pin. So basically on the IO side, so you have a cable. There are different colors. There's a definition on the hardware definition. So you just need to cut this cable and get for example, from here, I get these brown and pink and gray, which is the UART TX-RX and the ground signal, and connected to UART to USB connector. With this thing, you can connect it to the computer and use a serial monitor, and then you can already read the data output. On the CAN ports, which is actually not an output, it's only an input. So basically, you can connect the WIR sensor, odometry, WIR speed sensor, connected to the CAN, and this data will be as an input for the sensor fusion. And on the back of this device, there is a USB-C connector. This connector is for data logging. So you on this device, the memory is about 5 gigabytes. So it's like 30 minutes if you really record everything. If you record the image, videos, and their data, you can only record like 30 minutes. On top of that, if you want to read more data, then you can connect to this USB-C device to a hard drive, like 2 TB data. But of course, if you don't record the camera videos, if you only record the raw data, then you can record much longer. On the sync side, there is also a PPS output and trigger indication, as mentioned earlier. On the sensor fusion side, there are 4 different feed profiles to select. The first one is called automotive. So the dynamic is very similar to a passenger car. The velocity range is a maximum plus minus 22 meters per second, which is about 80 kilometers per hour. There's also angular velocity range and acceleration range. On the handheld application, so it's the sensor fusion. So it's like the human gaze. Basically, you hold this device and walk around. So it's like the mapping or the SLAM application. So the velocity range is much lower. The assumption is much lower. For the lawnmower, it's like a lawnmower robot. It's plus minus 3 meters. And on the slow mode, which is like the slow moving passenger car, so the velocity is plus minus 3 meters per second. And here is the Vision Navigator starter kits. So you will receive a starter kit like this. So let's see what's inside. So first, when you open this box, and you will see the Xsens Vision Navigator, which is this metallic device. This is the major component. Okay, so after that, you will have this aluminum frame with the suction cups. So these are the suction cups for you to attach to the glass or to the top of the car. And on the mounting device, there is also a cable, and there is a place to install the 2 antennas. So you will have the 2 GNSS antenna, which is a helix or dual antenna L1, L2. So basically, you just install it onto the left and the right, and afterwards you can connect to the GPS connector on this side. And there is also a Wi-Fi antenna. The Wi-Fi antenna is right over here. So when you connect to this device via Wi-Fi, this device is like it can send a hotspot of Wi-Fi. So you can find the Wi-Fi and can connect it to the Wi-Fi, and then visit use a browser like a Chrome or a Safari. Like you can actually connect via any device, like your mobile phone, your iPad, your computer. You just need to find the Wi-Fi hotspots, connect it, and just open with a browser. You can see all the data and also all the configuration. I will introduce later. On top of that, you can also have the power cable. The power cable is just connecting right over here. We have a battery as well. The battery is a 3,000 milliamp hour. So basically, I think you can use it for probably 1 or 2 hours. 2 hours, and you also have an Ethernet cable. So Ethernet cable just connected to this pin. On the other end, you will have these the normal pin cables, Ethernet cables. Just you can plug into your computer, or you can plug into a router. So, for example, here I can actually plug in this cable, this blue cable, to this router. And if my computer also plug into this router, then I can also visit via the IP address to this device. There's also I/O cable. I just show you. So there's this I/O cable. You can connect it to the I/O pin or the AUX X pin. So basically, you need to take a look at the definitions on the menu. That's the 2 antenna charger. That's it. The model is XVN-090D-1A-SK. All right, so I see. Okay. Yeah, if you have questions, just leave your message in the chat bin, in the chat message. Okay, so let's take a look at how to start to use this device. So basically, there are several steps. Firstly, you need to establish the network connection, which means you want to get this device online. So in order to get this device online, this device need to connect either from Wi-Fi or from Ethernet to the internet connection. If you connect to the Wi-Fi, which means that you connect with this, there is an antenna over here. It will, it can be act like a master or slave. So if it is acting as a master, which means that it sends out the Wi-Fi signal, and then you can use any device to connect it to configure it. But you can also use as a slave, which means that if you have a hotspot, for example, you have a wireless router or you have your iPhone's mobile hotspot. So this device can connect it to your iPhone's mobile hotspot and get it online. Why do you need to get it online? Because we need to use this RTK, the encrypt service. So basically, the encrypt service is kind of subscription service that you have to connect to the server with your subscription username and passwords. So that's why you get it online. But if you connect to the Ethernet, it's the same. So basically, this Ethernet needs to connect to the router, and this router needs to be online. After that, you can set up the Fusion state, configuration of Fusion, and then you can start a log. So let's take a look at it. So first step, if we connect it to the device by Wi-Fi, so basically this is my computer. I click right over here and on the Wi-Fi, and I can find this FP-8F11FA. That's the hotspot from this XVN, and you can connect it. After wire, you connect it, and you will have a IP address with your computer. Your IP address would probably be like a 10.0.1.5, and then you can visit this this device with this IP address 10.0.1.1. That's over the over Wi-Fi. If you are using the Ethernet, then the IP address would be 10.0.2.1. So after that, you just refresh. You can see from the browser, you can already see the interface over there. It's very simple to use. So after that, you want to configure the network to make it online. So basically over here, there's a button called networking, and then you can click the add new, and it will scan the network around you. You know, over here, if you have a lot of Wi-Fi network, then it could be difficult to find. So the rule of thumb is that you need to get outside where there's not too much of internet connection, Wi-Fi signals, and just open your Wi-Fi from your hotspot, like your mobile phone. Then you can find it and connect it. After you connect it, you will see your IP address. It also says over here connected, and you can also see the IP address. Yeah, so you can actually, if you have other devices in this local area network, you can also access to this device via this IP address. And on the Ethernet side, so on the Ethernet side, if you click down over here, and then if you are connecting this device with a cable to the router, you will also have an IP address, and you can also visit this device via the IP address. Next, you need to set up the RTK account for correction. So just click the configuration RTK. There's two options. There is a serial TCP. There's also encrypt client. So if you go serial, you have to connect this external encrypt modem, or we call it DTU, and get that device online, get that device with your username on the RTK subscription. And that device will send the RTK real-time correction message. And then you can connect that device, connect that cable. Oops. Let me see. Sorry. Oh, the power was down. Sorry. Now after this, So basically here, I just fill in my passwords, my username, password, and address. So this address is from China Mobile. So you have a lot of RTK service providers. Like in China, we have the China Mobile, Alibaba, and in Europe, I think there's RTK Go. In India, there's the National Survey Bureau. They also provide such kind of a service. You have to pay and to get the account, the address, server, and everything. So basically here you just click apply, then it's connected. After that, let's take a look at how to configure the Fusion. So right over here on the configuration, you click the Fusion. So on the Fusion, you can see here the first, that's the housing. So there are three modes. There's a standard, a weatherproof, customized. So weatherproof means that there could be raining days. So it's kind of a filter option for the camera itself to recognize the image situation. So standards might be the bright days. So for the tuning mode, you can see, So for the tuning mode, you can see the car, handheld, lawnmower, and the slower. And that's the translation sensor to GNSS antenna. On the Xsens Vision Navigator starter kits, so this distance has already been measured. So from the original point of this device to the antennas on the XYZ, it's being measured. So it's like the default values. So if you somehow install this sensor to other devices, then you have to measure it by yourself. So here there's a button. You can click this reset evaluation kit, which means that the value will be reset to the default values. And afterwards, you can see that's the output format. So basically, these are the stream reports that you can get for example, FP, Odometry, NMEA, FP, LH, and this like this one, FP, TF, VRTK camera. So that's the camera information, the images, also the raw IMU, the corrected IMU message. All of these messages are sent via the NMEA message. So basically, you just scan this port with this Ethernet port or the UART port. So here, that's the output frequency. As previously mentioned, the output frequency is maximum 200 Hertz. Here, the default value is 20. There's another concept called static transforms output frequency 1 Hertz, which is basically comparison information for people to understand whether there's a transform or movement happened in the past 1 second. So here is by default 1. And here you can also set up the translation sensor to output and the rotation sensor to output. So basically, this one, like the rotation sensor to output, is very similar to the MTI's rod sensor. So basically, you can rotate the XYZ, you can rotate the coordinate frames for this sensor. And next, that's the output we just mentioned. And next, we can check the GNSS reception. So over here, you have to get outside. Otherwise, you can never get any outputs. So you can see if you click the position and the GNSS status, then you can see the GNSS 1, which is RTK fixed, and the GNSS 2, which is still RTK float. So okay, so now you see the RTK fixed for both antenna, which means you can start Fusion and you can get outputs. Here, so start Fusion. So click the positioning. There's a Fusion status. Just click this button. There's also an option to set it up, and it will start Fusion automatically. So now it says started. It's very easy to use. So you can see the position on the latitude, longitude, and the altitude. Also the orientation, row, pitch, yaw. There's also two status, like the IMU bias estimation. It is converged. The IMU signal quality. If it is not converged, you have to do initialization. So by initialization, it means that for this IMU to find its bias, to find its dynamic. So basically, you can drive your car, or if you're walking, you can drive like 8 figures, or you can drive backwards and forwards within 10 meters. So after that, this device will most probably be reached into the status like the converged, and the IMU signal will be signal quality will be low. So here it says if it is indicated high over here, it does not mean the bad quality of the IMU signal. Just the signal level of vibrations is too high. For example, if you do this, just shake it up and down, you will probably see the high. Okay. And the next, you want to record your data. So on the system, there's a log. You click that log button, and you can see here on the record data, there are 3 options: the minimum, medium, and the maximum. So on the maximum, you will be able to record every message that you want, almost everything, including the image, camera, the videos. On the medium and the minimum, you will not be able to get the camera, the videos. So you can check the menu to see what kind of a message you will get on the on different recording modes. So after that, this yeah, you can see here. Yeah, start recording. So you can see the time, and then there is a file generated. So if you want to stop it, you click the system and the stop, and this recording will be generated. And this file would be in the .fpz. The .fpz is kind of a zip file, so you can just unzip with any zip software, and after that you can see these kind of files like this .fp and a .bag, and this .bag is the ROS bag format. So basically, you need a Ubuntu or Linux system to open these bag files, and if you have the experience with Ubuntu and ROS, so you can easily use the RQT bag tools to open this software to see the plot, see the data, and see the image. But you also have option to use other tools to export the file into like the TXT files, the videos. And if you record via the UART or via the Ethernet, then you can just record anything that you want. You can record the file into TXT files. So how does XVN do with RTK correction? So it can be either with internet or without the internet. The XVN can obtain the RTCM3 message. If you use the internet, so basically this device, XVN, needs to be online. Just like I mentioned, you need to connect to a Wi-Fi signal, like your mobile phone's hotspot, or you can connect to your wireless router. And on that case, in that case, you basically need to fill in your entry confidential credentials and to connect to the web server of this entry caster. And this entry caster could be like the China Mobile, Orange, or Indian Survey Bureau. These companies or organizations who provide the entry correction service. Otherwise, you can use the external device. So this external device, you can connect via the TCP. So basically, if this device, we call it DTU or entry modem. So this entry modem needs to be in the same local area network, and then you can find each other. Basically, you can subscribe the data from the IP address. Otherwise, you can connect via the UART, basically the RX, TX, the GND, and then you can also receive the RTCM message. The next is a wheel speed sensor. So the auxiliary sensor configurator supports up to 4 external wheel speed sensors currently. So each sensor requires a correct definition to be used as input to the sensor fusion engine. So basically, you click the system auxiliary. On the auxiliary, you can see sensor 1. Click enable the name RC, for example. So RC stands for a rear center. So that one could be for like 3 wheels robotics. But for the cars, you only have 4 wheels. So you will have FL, front left, FR, front right, a rear left, and a rear right. So you need to fill the exact name like this RR or RC, and then the type, the device. If there's a translation needed, next that you can add the sensor, extra sensors. Okay, so sensor configuration, everything, you can find everything in the menus, mti.docs.xsens.com. So you have 3 menus. The quick start guide is the first menu that you want to read when you receive the XVN. The datasheet, the information, the integration menu, the very detailed information, also the ROS driver. Again, this is documentation. There's a leaflet. Actually, I put it in the handouts. If you can see it, you can also download. But I imagine the account executives like Kenny or Chandra also send to you guys. There are several FQs. I didn't see any question from you guys, but I can read some of these FAQs. I will send these slides to you guys. So, for example, the IP level for the Vision Navigator, that's the IP66. What kind of RTK correction protocol? That will be the RTCM v3 over the N-trip or UART. So the providers could be like the Qianxun, which is the Chinese one, SweetPost, maybe the Swiss ones. And there's also support for the wheel speed inputs. Output of the internal IMU, yes, you can get the IMU data from the TCP interface, also the UART interface. How long can the localization be stable without RTK GNSS fix or general GNSS signals, assuming we keep moving at a constant speed, say inside a tunnel? So the RTK drifts relate to the driven distance at a rate of 0.5 to 1% per travel distance. And does your solution work in darker room areas, darker indoor areas at night? So the solution was tested in better illuminated environments like in parking garage, evenings and transition of indoor and outdoor situations, including blending sunlight during the day. All situations are handled by our system without a major degradation, but pure darkness can lead to degradation when no GNSS is available. So what is the requirement to start and initialize a sensor? The requirement is, as mentioned, you need to have both GNSS antenna to get RTK fix. Okay. Interface, again, Ethernet, Wi-Fi, USB, UART, CAN is only for input. The speed, that's about 80 kilometers per hour. What happens if it has a higher velocity? So if going too fast can be a problem for camera feature tracking and achieving RTK fix. That's for the antenna, and that's for the camera. During outage, the performance can degrade. Our customers' use case are usually at a lower velocity anyway. And the data, so as mentioned, if you don't store camera image, you can store several hours. But if you store the camera, then that's about half an hour. That would be like 5 gigabytes. So the maximum option recording has images. The other options don't have images. And please use like a Samsung 2T drive if you want for longer hours. Is the internet RTK correction is mandatory? Yes. You either need to use the internet or you use the RTK correction from the RTK base station, Okay. So here, this is the drive that I did this morning. So firstly, I have achieved the RTK fix. Start a Fusion engine. And click here, start to log. And then I start a drive. You can see you can actually also overlay the map. So this map is from Mapbox. It's also pretty accurate. I think my location was exactly on this lane. I was driving on this left lane. It's exactly there. And over here it's an open area. You have a very good GNSS reception. That doesn't matter. So I drive right over here. You can see there's a this is the train road. There is a tunnel over here. So when this device gets into here, you will not see the red. You will not see the yellow and the blue dots. These stand for the GNSS 1 and the GNSS 2. So you can see even there is no GNSS, this line straightly follow the way, the trajectory that I was driving. There was no deviation at all. If you had experience with testing MTI 670 or MTI G710, 680, you can see more or less there will be some drift on this lateral direction. Yeah, this is perfect. So next, I drive all the way around to the second circle. So you can see these two lines from the first time and the second time perfectly overlay to each other. That's thanks to the dual antenna RTK. So imagine that I haven't installed the wheel speed sensors yet. If I install that, I imagine this line could be even better. Again, we're gonna go into the tunnel. So on this tunnel, that's about 30 seconds. All right. Yeah, you can see there's almost no drift. Okay, I did another circle again, which proves to be really accurate. And next, I want to show you the underground garage. So basically, this is our company office in Shanghai. So right over here, I drive into the underground garage. So very quickly, you will see there will be no GNSS reception from this point. This is like the entry of the underground garage. So make a left. And then make a left again by 90 degrees. And next, I made several circles underground. So over this area, it's totally on the camera and the IMU fusion. There's no GNSS at all. No RTK, no GNSS. You can see there's a minor difference, but not too much. This is like the second. The third and fourth. Now this is for me to drive backwards and into the parking position. So you can see after several circles, there's a very tiny difference, but not really much. And this is when I'm driving backwards into the parking position. So in general, I think this is a really, really good tool for evaluation for autonomous driving. If as long as you're not driving too fast in the tunnel, for example. I mean, if you're driving really fast outside, that would be mainly on the RTK, GNSS, and the IMU sensor fusion. But if you're driving into the tunnels, well, there are not too much of GNSS, but you're not also not driving really fast. Most of the cases, you're driving less than 80 kilometers per hour. So you have large chance to use this for autonomous driving use cases. Also, for the application where you have indoor and outdoor, imagine that if you get outdoor, you can have the RTK GNSS correction again, and if you get in here, you get a correction. The position will be much more accurate again. Yes, I think that's it for my presentation. Do you guys have any questions? Question. In case above 80 kilometers per hour, XVM may degrade the performance you told. Is it only GNSS signal outage? In case good GNSS reception above 100, it will not be a problem. Yeah, I think